Okay, this is section 4.3, how derivatives affect the shape of a graph. So the first thing, and I think we've talked about this before, is that if the first derivative is positive or greater than 0, then f is increasing. So that means that the slopes are positive, so that means that the slopes of the graph are also positive, so we get an increasing function. If f prime of x is negative or less than 0, then f is decreasing, which means it's declining, and the slopes are negative. The first derivative test says that if f prime changes from positive to negative, so let's just take a little look at that. So positive slope to negative slope at x equals c, then f of c is a local max. And if f changes from the other way, from negative to positive, I think you can see that that creates a local min. So what you want to do for the first derivative test is find the first derivative, set it equal to 0, and then make a sign chart. Next we have the test for concavity. And what concave up means is pretty much exactly what you think it means. Also, an inflection point is something that shows the change in concavity. So you can see here in this little graph that we're going from concave down to concave up, and that's called an inflection point, which we will abbreviate IP. And what we have is this is information coming from the second derivative. So if the second derivative is greater than 0, then we're concave up. Our function is concave up. F is concave up. Not the second derivative, but you're using the second derivative to infer something about the actual function. And so if the second derivative is less than 0 or negative, then f is concave down. The second derivative test, you set the second derivative equal to 0 to do this. But the second derivative test tells you that if f prime of c equals 0, so this is where you have a horizontal tangent, and you have concave up, then f of c is a local min. So we're concave up, and the derivative is 0 at the point. There's my c value. That should make sense that it's a local min. And similarly, if we are concave down, if we are concave down and have a horizontal tangent, then we have a local max. Okay, so let's do an example. We want to find where f is increasing and decreasing. So we do that by taking the first derivative and setting it equal to 0. So the derivative of f of x is 6x squared minus 18x plus 12. And then if we set that equal to 0, we get 6x squared plus 18x plus 12 equals 0. I think I want to divide all of that by 6 to make it a little easier to manage. And this factors x minus 3, x minus 2, x minus 1, multiply together to give us positive 2 and add to negative 3. So we've got x equals 2 and 1. These are critical values. And I just spelled values in a really weird way. Values. There we go. Okay, and so what we want to do with that information is we want to make an x-axis here and make a sign chart. Here's 1, here's 2, and I want to look at the signs of f prime, and we can do that by looking at the signs of x minus 2 and x minus 1. So these, ultimately, the first derivative here factors to 6 times each of these. And so these are the zeros, where the derivative is 0 and where we have a horizontal tangent. I do want to point out really quickly, so that I don't forget, is that we set the derivative equal to 0 or undefined. So we don't set it equal to undefined, but if the first derivative is undefined, then we get critical values. So keep that in mind. This is a polynomial and doesn't have any undefined values for x, and so therefore we don't have to worry about it for this one, but generally it should be something that you take into consideration. That will give you critical values. If there's an asymptote or a hole in your graph, then the increasing and decreasing could change on either side of those. So you need to account for those as well. Okay, so back to our graph over here, or our sign chart. X minus 2 is 0 at 2. So it's negative before that and positive after that. This is a linear factor with positive slope. X minus 1, similarly, it's 0 here at 1. So before that it's negative and after that it's positive. And f prime comes from the product of these two. So we're going to have a negative times a negative. Let me erase that dot. The negative times a negative, and we're going to get a positive. Here we'll get a negative, and here we'll get a positive. So here in this row, we have the signs of the first derivative of f, which means that we're going to be able to tell something about f by looking at that, and that's that we're increasing in this interval, decreasing in this interval, and then increasing again in this interval. Typically continuous functions will alternate like that. So this point right here, you can see it's going to be a min. But I wasn't asked that, so I'm not going to do that just yet. Where is f increasing and decreasing? I think we did answer that question, but let me write it up more formally. So f is increasing on, and we've got the intervals from negative infinity to 1 and 2 to infinity. F is decreasing elsewhere, or more specifically between 1 and 2. Let me seal this off a little bit. Okay. So local mins and maxes, I think it's really obvious, and I don't think we need to do a second derivative to show this. Not in this case. It's not always super duper clear, but in this case, I think it is super duper clear that there is a local max at x equals 1. And so we need to evaluate f at 1 to figure out what that max is. And if I scroll up a little, that's going to be 2 minus 9 plus 12 minus 3. So that's going to be 2. So local max of 2. And then there's a local min as well when x equals 2. And then if we evaluate f at 2, we get 24 minus 36 plus 12. I think that's 0. Let me double check that. My notes say that it is 1. Let's see, 2 times x cubed. I did 3 times 8 instead of 2 times 8. This should be 16. And then 16 minus 36 is negative 20. Plus 24 is 4. Minus 3. Wait, what am I looking at? 16. I forgot the minus 3. I did all kinds of weird things here. Okay, so I've got 2 times 8, which is 16, minus 9 times 4, which is 36, plus, this one should be 12, times 2, which is 24, minus 3. So we get negative 20, we get 4, minus 3 is 1, and that is consistent with my notes. So here's our local min. And it probably makes sense to write these as ordered pairs, 1, 2, because we're going to graph this later. 2, 1. These are our critical points. Now, concavity, we do already kind of know, because we already know that the graph is doing this. Okay. So we have some sense that it's going to be like this is right here, this is happening at 1, and this is happening at 2. And so from there we can kind of see where the concavity takes place. But let's go ahead and use the second derivative, set it equal to 0 to confirm what we've done. So I'm going back up to look at the first derivative. It's right here. And we have the second derivative is going to be 12x minus 18. And we can take a 6 out. 2x minus 3. So when we set the second derivative equal to 0, that's going to happen when 2x minus 3 equals 0, or x equals 3 halves. F evaluated at 3 halves. I don't know. That's going to be, I should have calculated this one, but I didn't. It's okay. I'm going to go ahead and just skip right to the second derivative test. Well, we're going to do a sign chart again for the second derivative. Now we just have 1 point. And the second derivative is going to be negative and then positive after it's 0 here at this x value. And so we are concave down and then concave up, which is completely consistent with what we'd already learned from doing the first derivative. So to graph this, I think I do need to evaluate my 1.5, but I think I'm going to just type it into, I don't feel like doing the fraction right now. Let me see if I have. At 3 halves, it's at 1 point. I think. Let's see. That might take me too long. So let's just do a quick graph. So I'm looking at my critical points, 1, 2, and 2, 1. Let me go ahead and put in some y values. So 1, 2, and 2, 1. This is a max. This is a min. We know at 1.5 we're going to get a change in concavity. And that really isn't enough to get a super good picture, but if we add things like the y-intercept, so when x is 0, f is -3. So that's going to be down here. And we also know that there aren't any other maxes or mins, any other places where the first derivative is 0. So we know it's going to come up, it's going to come down, and then it's going to go back up. And that's pretty much what our graph looks like. Our inflection point, it looks like it's at about 1.5, but that's an inflection point, and that is, I don't want to make it look like it ends down here. It keeps going down. Okay, so we'll continue this next time. I just wanted to give the background information. I think I have one more example that we can work in class, 1 or 2 more examples, and I'll see you on Monday or Tuesday.